Hi everybody, I'm Alan Goldstein from the University of California, Berkeley. It's really a pleasure to be here today. Thank you to Paula and the Sloan Foundation for funding all the research I'm going to tell you about. Thanks to AAAS for having us here. And thanks to the people in this picture for doing all the work I'm going to show. It's really their work. This is a bunch of my graduate students and postdocs, plus a very close colleague, Bill Nazaroff, who's been a leader in the field of indoor air for his whole career, who recently retired, actually. So I'm going to be talking about bringing atmospheric chemistry home. Now, there's been a lot of work in atmospheric organic chemistry, and I've been spending my career at the heart of that work. I wrote what's really a review paper with Marianne Glacias a couple of years ago, and I want to point out a couple things from that perspective on outdoor air. First of all, we say in the outdoors that the Earth's atmosphere has a huge array of organic compounds. They differ by orders of magnitude in terms of their properties such as size, volatility, reactivity, and the chemistry that they go through, and their impact on climate and health. And so this picture just shows kind of how we think of the outdoors. There's lots of different sources of VOCs, volatile organic compounds. Some of those are natural, some are anthropogenic. They react by being oxidized in the atmosphere, forming a lot of semi-volatile organic compounds, which means they tend to be lower volatility. Some of those can stick to particles or surfaces, and we form these secondary organics that are really important for health, for visibility, for climate. And so in trying to explore this chemistry, the analytical toolbox that we've developed has grown dramatically. There's been really a revolution in mass spectrometry and in the tools that we use to get atmospheric chemicals collected into mass spectrometers over the last decade or so. It's just changed our view completely of outdoor atmospheric chemistry. But I spent the past 3 decades studying this, largely justified by human health concerns. And the fact is that we spend 90% of our time indoors, and 70% of that time is in a residence. And so with Paula's instigation of the Chemistry of the Indoor Environment program, I got pulled in to start looking indoors. And so I say that we've been bringing atmospheric chemistry home, applying this analytical toolbox to understand the environment where we spend most of our time. So indoor air does not equal outdoor air. Buildings are leaky. Sometimes we open windows and doors and we deliberately exchange the air, but even when we're not doing that, there is air exchange through the cracks in the building. Outdoor air impurities can be altered when the air is brought indoors, and indoor emission sources can strongly influence indoor composition. And I can tell you right now, the largest source of organic chemicals in this room right now is all of you. What's the state of knowledge? We just heard a lot about this from Rich, but I want to point out just a few features. One, we know a lot of things are elevated indoors. 2, those sources include building materials, furnishing, occupants and their activities. But we've really got limited knowledge about source rates, chemistry, and dynamic behavior, and that's largely because the tools that we've had in the past to apply to studying indoor chemistry. So the strategy that we've taken in my group at Berkeley is observe, don't perturb, do detailed investigations at a few sites in normal use, do really high resolution measurements in terms of time, space, and chemical species, and then try to understand the processes that are going on at a very fundamental level so that we can model them in the future, working with the Mochi team that you'll hear from later, or Moki, sorry, Manabu. And we want to investigate the processes, especially for the emissions, the chemistry, and the exposure. So I'm going to show you a little bit of data and tell you, bring you through a story of what we did in one of our very first outings as part of this program. We did residential sampling campaigns in California in normally occupied wood frame single-family homes with no indoor air quality problems that were known. We looked at houses that were built in the 1930s and 40s, which are typical California residences. H1, we looked in the summer and the winter. And H2, we just did the winter measurements. And we measured everything we could. So this is just an example. We put wireless sensors all over the house. We could see where all the occupants were and what they were doing. We had motion sensors. We had sensors on all the appliances, windows and doors, to see if they were open or closed. We had temperature and humidity sensors everywhere. We had the occupants write down everything they did. We measured particles. We did biological sampling. We got at air exchange rates. And we measured lots of trace gases, but I'm not going to talk about any of that. What I'm going to talk about is my favorite subject, the organics. So we're going to talk about volatile organic compounds and semi-volatile organic compounds. Rich introduced both a little bit. I won't go into the instrumentation that we're using for VOCs too much, except to say that we can measure hundreds of species in real time with concentration detection limits down to around a part per trillion and time response of seconds, okay? So let me show you first some VOC data. And I'm going to point out that we set up a single instrument with sampling lines to 6 different places, and we switched every 5 minutes between those places. One was outdoors here in red, then in the crawl space, which is below the house, the basement, which is at the bottom of the house, the kitchen and the bedroom areas, and then also in the attic, which is the space above the house. And we did a summer campaign and a winter campaign. Most of the time, the space was occupied, and sometimes it was vacant, here in yellow. We just plotting here the sum of all the VOCs that we measured, and note this is a log scale. And a few things should pop out immediately, and I was shocked when I first saw this data, and I hope some of you are too. The first thing to notice is that the outdoor concentrations of the sum of all the VOCs were always an order of magnitude lower than the spaces where we spend our time indoors, in the kitchen and the bedroom. The air in this house is flowing generally. We know this from our tracer release studies. The air is flowing up from the bottom to the top. It goes into vents that are in the crawl space and goes up into the house, into the living spaces, and then out the windows and up through the attic. And so one of the things that's really interesting is that crawl space in the basement, the concentrations are very similar to the outdoors, but the bedroom and the kitchen are really high, and so is the attic. That tells us something really important, that the sources of those VOCs that are indoors have to be coming from indoors. There's no way they can be coming from outdoors, first of all. Second thing I want you to notice about this is that when the house is vacant and when the house is occupied, you see one major difference, and that is no spikes. The average concentration, the lowest concentrations we see indoors, hasn't changed much when you're not doing anything inside the house, when the people aren't there. But the activities that the people were doing when they were in the house were causing these spikes. That tells us that this high background is coming from the stuff in the house. And on top of that, people are doing things, cooking, cleaning, et cetera, that's adding these spikes. So that tells us the continuous emissions from the indoors are really large, and that occupant activities occasionally cause spikes. Another thing you'll see here is that the winter and summer data don't look all that different. So now let's go a little more specific into the chemicals that are there. This is just comparing the average concentration in the summer versus the winter for chemicals that were in the kitchen. They're colored by their mass to charge ratio, so going from small molecules to big molecules, basically. So think of that as molecular weight. My very favorite molecule is the top one, ethanol. And it turns out that ethanol concentrations inside the home, summer or winter, averaged 100 parts per billion, which is shocking. It's really high. Outdoors, in an urban area like Los Angeles, you can expect to see 3 to 5 ppb of ethanol. Okay, so that's really high. Acetic acid, methanol, all of these relatively light, oxygenated volatile organic compounds are very high in the house. There's a lot of other chemicals there. One other thing I want to point out, though, is that the winter and summer are mostly the same. Two things stick out in the winter that were higher. One of them is called D5. First, how many of you are wearing antiperspirant? Come on, be honest. A lot of you. Okay. That D5 is cyclic methylsiloxane. It's the dominant ingredient in your antiperspirant, most likely. And it's probably also the dominant volatile organic compound in this room, which means that the dominant VOC in this room right now is coming from your neighbor's armpits, and you're sharing it with them, okay? And it turns out that one of the occupants in the winter got a new product that had D5 in it. It's a common product. It's a common chemical in personal care products. And they put it on, and that elevated concentration is from some of those spikes. Monoterpenes. Rich talked a lot about monoterpenes. When we think in outdoor chemistry about monoterpenes, we think those are some of the dominant chemicals emitted to the atmosphere. They're dominantly emitted by forests. And they react in the atmosphere and are the major source of secondary organic aerosol in much of the US, particularly the southeast US. A typical outdoor concentration in a forest of monoterpenes is less than 1 part per billion. The average in the summer was a little over 1 part per billion in the kitchen and 10 parts per billion in the winter. Why? Where do these monoterpenes come from? First, that's that beautiful lemon smell, or citrus smell that you have in a lot of cleaning products, but also it's coming from citrus itself. And so the occupants in this house only eat fruit when it's in season. Oranges are ripe in the winter. They're eating a bunch of oranges, and that's from eating oranges that you get 10 ppb of monoterpenes in the house. Okay, so moving on, we invited a bunch of people over for a party. And I show this slide to demonstrate what we can learn with really high high time and response data. So we had all these sensors going. You can see that people woke up in the morning. This is one day. They woke up in the morning. The motion sensor saw them come into the kitchen. They turned on the coffee maker and the toaster. Pyridine is a chemical that's really ugly. It's a benzene ring with a nitrogen in it. And you'd look at that chemical, if you think about health effects, you think, that can't be good for you. It turns out it comes from your coffee. And so it's part of the aroma of the coffee. The ethanol spiked also at that moment. What were they doing? Was that Irish coffee? No. It turns out that they made toast. And bread is a fermented product. And it has a bunch of ethanol in it. And so when you heat it up, the ethanol comes out. And so we see that spike, right? We go a little bit later in the day, and they start cleaning, and we see solvents starting to come out. We see ethanol and acetone. A bit later, they start cooking, and they made ratatouille, so a bunch of vegetables sauteed in oil, and you see lots of sulfur-containing compounds, this ethane thiol plus DMS from the cooking. So then, it's about time for people to show up for the party, right? What happens? Several things. First, everybody got cleaned and dressed up and reapplied all their personal care products, and the D5 spiked as soon as everybody walked in, right? Then they heated up the food, the ethane thiol, DMS comes out, and they start opening the beer and the wine. And the ethanol went up to 4,300 parts per billion in the house, 4.3 parts per million. That's huge, right? That's really a lot. People left, they started cleaning up, and there's another big spike of ethanol. I don't know if they started drinking again. But I think what they did is they took all the half-empties and they threw them in the sink, and you see this big burst of ethanol come out, right? And at the same time, they started washing the dishes, cleaning up, and you see chloramine coming out. So chloramine is coming from the treated water that's coming in through the tap. And then just a little later, they turn on the dishwasher, and lots more chloramine comes out. And so what you can see here is that with high resolution chemical measurements, high temporal resolution, we can actually look at what's emitted from all these different kinds of events that happen indoors. And we're integrating this and looking at the full chemistry and working on papers that actually say what chemicals come from what kind of activities, how much, and then trying to understand how that matters. So one point I want to make, oh, you're kidding me. Wow, that can't be right. So, no, really, I don't think I could have possibly talked for 14 minutes. But anyway, so we have, when we look at the spiky pattern, what you see is that the spikes in all the VOCs that we measure follows the exact pattern of burner uses in the house. So in other words, most of the spikes that we saw in the data were coming from cooking. And you can see there's a spike at breakfast, lunch, and dinner that is persistent. And if we add up the continuous emissions of all the things that weren't spiky, the things that were at least 10 times as high indoors as outdoors, we see actually that we get a total emission that, I won't go into the numbers too much, but I'll just say that the total emission doubled over a 7-degree temperature range. And so this is the background emission in the house. And that background emission is actually really high. And one of the things you'll hear later from Matt Coggin and maybe some others is maybe all these emissions matter when they get outside. Okay, so Ray, did I really use up my time? I don't think so. I don't think it's possible. Okay, just go. Okay, sorry. Wow, I'm just too excited, I guess. So let's say a few words about semi-volatile organic compounds. I won't get deep into the methods of how we measure these, but the instrumentation that we developed to measure these, we actually invented in my lab. And the questions are, what are the SVOCs in the home? How do building characteristics affect the source's chemistry and dynamics? And then how does occupancy and activity affect concentrations? And semi-volatile compounds are sticking to all the surfaces. They're coming off the people, off the furniture, from cooking, from outdoors, and we want to understand their dynamics. When we look at a chromatogram of the semi-volatiles indoors, what we're seeing is the stuff that comes out early in the GC retention time is the lighter stuff, and the heavier stuff, the more sticky stuff comes out later. This is a really crazy chromatogram. For any of you who do this kind of analytical chemistry, you realize that that's a really, really full chromatogram, lots of different chemicals in there. We can pick out individual ones, and here are the phthalates, for example, and some other compounds that Rich talked about. And we can see that there's lots and lots of different chemicals with different functionalities here. I'm going to just go into detail on a few. But first, I want to say that this is what the outdoor SVOC chromatogram looks like. And when you go indoors, it looks like that. The phthalates that Rich was talking about are like a needle in a haystack. They're just one of many, many, many thousands of chemicals, actually, that are there. So when this is happening indoors, you think, oh my God, I should clean this place, right? What happens when you clean? It turns out that you actually increase the concentration of a lot of these things. Why? Because you're putting a solvent on these surfaces that are covered in organics, and you're changing the pH, and you're liberating a lot of them into the gas phase. Wow. Let's just cook dinner and relax about all this, right? So what happens when we cook dinner? It looks like that. And you get way more chemicals, and we're getting to heavier chemicals. Stearic acid comes from cooking with oil. Cholesterol comes from cooking meat. And a lot of these are in the particle phase. When we look at the total SVOCs as a function of time, we note a couple of things. One, there's a wiggly pattern here, and I can just tell you that that follows temperature. That's because the heating system is going on and off to maintain the temperature of the house. The vacant period and the occupied period look pretty similar, but there's extra spikes in the occupied period. Most of those spikes have to do with cooking. You can see the cholesterol and stearic acid coming from the cooking, and that's mostly in the particle phase. And so those get flushed out of the house really quickly when they're in the particle phase. But then when we clean, we see some nonanol and terpineol, and those go away much more slowly. This is why when your house gets cleaned, you come back a day later and it still smells clean, right? So you can all realize that that's going on, but the gas phase compounds leave much more slowly than the particle phase compounds. Just a couple more slides. I really am amazed if I did that. Okay, yeah, okay, sorry. Indoor SVOC concentration is driven by temperature. And if you look at the integral of all the SVOCs, what we see is that it really follows temperature. And the only time that total SVOC doesn't follow temperature is when we have cooking, cleaning events, or candles. And so there's a background level of SVOCs that's driven by uptake and release that's temperature-driven equilibrium with surfaces. So one thing that we might want to do is we might want to vent the house and flush all those VOCs outside, right? So we did an experiment where we vented the house, and this is the total SVOCs indoors, and this is outdoors. You can see that indoors is 5 times as high, and when we vent, we can get it down to the outdoor levels, but as soon as we close all those doors and windows, within about 5 hours, we're back to where we were, because there's a huge reservoir of organics on all the surfaces. Okay, so bringing atmospheric chemistry home, I'll just put this up as a little summary to say that we've been applying all these new analytical tools, and we're learning a lot. And one of the things that we're learning, one of the main things we're learning is that occupant activities do contribute to the VOCs and SVOCs indoors, but most of what's there is there whether the people are there or not. There's a huge emission of VOCs and SVOCs that is temperature driven. There's a lot of chemistry involved, and the volatility of those compounds is really key to their behavior. I'll stop there.